Hello everyone. What we'd like to do in this video is take those sine and cosine graphs that we learned in the last video, and we want to know how to shift their graphs or how to transform their graphs. If you have seen function transformations or you're comfortable with function transformations, you're going to find that this section really isn't any different than how we normally transform functions. It won't be any different than how you transformed the toolkit function x squared or root x. We're just going to be applying it to a new function. Specifically in this video, the transformations we're going to look at are vertical shifts. How do I shift a sine and graph function up and down? How do I reflect a sine and cosine graph, specifically over the x-axis? And how do I vertically stretch and compress a sine and cosine graph? So when I'm doing these transformations, specifically with sines and cosines, there are a couple key features of those graphs that I'm always keeping in my mind. So let's say we have the function. Let's just do sine of x for right now. Let's just draw a quick sketch of it. So oftentimes I'll only graph one period. So remember, the period of sine and cosine are both 2 pi. Now how I'm going to mark this x-axis is going to be something I'm going to be doing quite often, or the strategy that I'm using to mark the x-axis is going to be important, specifically when we start changing the period of these graphs. So I'm always going to mark the period 2 pi. I'm going to cut that in half. I'm going to cut that in half again. So half of 2 pi is pi. Half of pi is pi over 2. And I'm going to cut my x-axis into 4 equal intervals when they'll have an equal width of pi over 2. So 1 pi over 2, 2 pi over 2s, 3 pi's over 2. The amplitude, I haven't talked about that yet. The maximum value of sine is 1, and the minimum value of sine is -1. Sine of 0 is 0. Remember, sine measures the height on the unit circle. So at an angle of 0 radians, the height is 0 on the unit circle, and will bounce between these corners. Okay, so the graph of sine of x looks like this. Here's one period. Okay, let's instead graph. Oh, before I go on, I'm sorry, I want to mention some key features. Notice that there's kind of like, I would say, like the average value or the middle value, kind of this line where this, I don't know, it's not really symmetric, but I would say the middle of the graph, this would be the x-axis. This line right here, this line is what I'm going to call the equilibrium. If you want to imagine there's some sort of hanging spring, for example, if we have the spring at rest, it would be at equilibrium. If I move the spring, if I move it up, and if I move the spring up and I let it go, it's going to bounce between, it's going to go up and down, but it's going to basically move up and down an equal amount from its equilibrium. So here's the middle, it's at equilibrium. And now the upper part of the graph, I know if you were like a surfer and you want to know the height of this radical wave, well, the distance from the equilibrium to the tip of the wave, this distance here, is what we'll call the amplitude, maybe a different color. Equilibrium. Let's use red. This distance, move this out a little bit further. The distance from here to here is what we'll call the equilibrium. I'm sorry, the amplitude. The amplitude. It's the amplitude of the wave. So the equilibrium is the middle, and kind of the height of the wave would be the amplitude. So if you measured from the equilibrium to the tip of the wave, this would be the amplitude. It would be equivalent if you measured from the equilibrium to the bottom of the wave. This would be the amplitude. I'm always paying attention to the equilibrium and the amplitude when I'm graphing graphs of sine and cosine. So, for example, let's erase a little bit of this here. Let's say that we want to sketch a graph of f of x, which is equal to, how about sine of x plus 3? So what is this graph going to look like? Okay. 2 pi, cut that in half, I get a pi. Pi over 2, 1, 2, 3 pi's over 2. Okay. So when I add 3 to the outside of the function, what we're doing here is I'm taking all my normal outputs of sine, and I'm adding 3 to them. So that's going to take my graph, and that's physically going to move it up 3 units. If I was subtracting 3, it would take all my outputs and move them down 3 units. So I'm going to be paying attention to specifically how the equilibrium has moved. The equilibrium was at 0, and now it's been shifted up 3 units. So I'll draw my new equilibrium. Boom, boom, boom. Here it's at 3. Okay, so our new equilibrium. And then from our equilibrium, I'm going to go up and down the length of the amplitude. The amplitude for sine and cosine untransformed is 1. So I'll go up 1 from equilibrium, and I'll go down 1 from equilibrium. So I know that sine of x plus 3 is going to live in this window. And then I'm just going to bounce off those spots on the unit circle like we normally do. Okay, so sine starts at equilibrium, and then as we go around the unit circle, the y-coordinate increases. So I'm going to initially start by going up, and then we're going to bounce off those spots. So here's the graph of sine of x plus 3. So it's been shifted up. Notice my scales aren't the same on these graphs. But I've taken this graph and I've shifted it up for units. I'm paying attention to where the equilibrium is, and I'm paying attention to the amplitude. Okay, let's do a different transformation. So we just did vertical shifts. Let's do reflections. Okay. So let's say, for example, I have the function f of x. Let's graph cosine. Let's graph cosine of x. Okay. Cosine also has a period of 2 pi. So here's pi. Here's pi over 2. Here's 1, 2, 3 pi's over 2. Okay. Cosine still has an amplitude of 1. Okay. The equilibrium will still be at 0 for cosine. Okay, cosine of 0, the x-coordinate at 0 radians is 1. So cosine starts at the upper part of the amplitude. And as we move around the unit circle, the x-coordinate decreases. Okay, so it decreases initially. We're going to bounce between those spots. So here's a graph of 1 period of cosine. Now let's graph f of x. How about we call it g of x? Something different. Let's put a negative out front. Negative cosine of x. So what's that going to do to my graph? 2 pi. Here's pi. Here's pi over 2. 1, 2, 3 pi's over 2. Okay. Well, what's going to happen? Well, what we're going to be doing when I throw a negative on the outside of the function, I'm going to take my normal cosine outputs, and then I'm going to multiply them by a negative. So I had my normal cosine outputs, and then I multiply them by a negative, so it's going to reflect it over the x-axis. I have these positive x values, I'm making them negative, I'm going to reflect over the x-axis. Or if they were negative, I multiply by a negative, that's going to make them positive. So when I put a negative on the outside of a function, that's going to reflect it over the x-axis. So if I'm graphing negative cosine of x, okay. Well, cosine normally starts at the upper part of the amplitude. Since it's being multiplied by a negative, it's going to start at the lower part of the amplitude, and then we're going to bounce, and then we'll connect. And there we have it. There's the graph of negative cosine of x. Okay. Let's go ahead and do a quick example. Let's have you try to graph. How about graph negative sine of x? Let's say minus 4. Okay, go ahead and pause the video and give this one a shot. Okay, let's do it. So what I'm going to pay attention to, I'm first going to pay attention to where my equilibrium is. I've taken the sine graph and I've subtracted 4 from it, so my equilibrium is at negative 4. So here is negative 4. Here's our equilibrium. Okay, my amplitude is still 1, so I'll put a negative 3 here, and a negative 5 here. The amplitude will still be 1. So this graph lives in this window. Let's mark 2 pi, pi, pi over 2, 1, 2, 3 pi's over 2. Okay. So let's think here. Sine starts at equilibrium. Now normally sine would then go up after, but since I'm multiplying it by a negative, it's going to go down. And here we have it. Here's the graph of negative sine of x minus 4. Okay, let's talk about our last transformation that we'll do in this video. How do we vertically stretch and compress a graph? Okay. So as an example, let's say, I don't know, let's graph sine again. So f of x is equals sine of x. Here's our sine graph. We've got our equilibrium in the upper and lower parts of our amplitude. Okay, so let's go ahead and instead of graphing sine of x, what if we had, let's say, 2 times sine of x? So how is this going to affect the graph? Well, I hope you believe that what's happening is I'm taking all my sine outputs, all my outputs of sine, and I'm multiplying them by 2. So what's going to happen is that's actually going to stretch my graph. If I multiply everything by 2, that's going to increase my amplitude. That's going to make my amplitude go from 1 to negative 1 to 2 to negative 2. So multiplying the outside of the function by 2 is going to change my amplitude. So here is 2 pi, here's pi. Here's pi over 2. Here's 3 pi over 2. Okay, so now sine is still going to bounce in this window. Okay, it's going to start here, and now it's going to bounce on the upper parts, on the upper and lower parts of the equilibrium, of the amplitude. And there we have it. There's the graph of 2 sine of x. Now instead, let's say we're graphing, maybe I'll do it in red. If we wanted to graph, let's say h of x would be equal to 1/2 times sine of x. Now that's taking all my outputs and multiplying them by 1/2, so that's going to compress my graph. So here I would have 1/2 and negative 1/2. That's going to decrease. It's going to decrease my amplitude. So I'll have a squished sine wave. Okay, so this would be 1/2 times sine of x. So the number multiplied out front will tell you what the amplitude is. Okay, let's do an example of combining all 3 of these together. Okay, I want you to try to graph. Let's graph f of x. Let's say it's negative, how about negative 4 cosine of x. How about plus, I don't know. How about plus 2? Sure. Okay, go ahead and pause the video and give this a shot. Okay, let's do it. So what am I going to pay attention to? I'm going to pay attention where the equilibrium is. I'm going to pay attention to what the amplitude is. Okay, so my graph is being shifted up by 2 units. So 1, 2. So here's my equilibrium. Here's our equilibrium. It's not mine, it's ours. Okay. Now my amplitude, you can ignore the negative. The amplitude will always be the absolute value of the number multiplied out front. So the amplitude is 4. So from my equilibrium, I need to go up 4 units. So I'll be at 6, and down 4 units. So I'll be at -2. So here, we have the window that this graph will lie within. Okay, we'll have 2 pi. Here we'll have pi. Here we'll have pi over 2. And here we'll have 3 pi over 2. Okay, let's see, cosine. Cosine normally starts at the upper part of the amplitude, but I'm multiplying it by a negative, so it'll start on the lower part of the amplitude. And then we're going to bounce. Bounce, 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 bounce. And there we have it. Here's the graph of one period of -4 cosine of x plus 2. Hope you enjoyed this video. We'll see you in the next one. In the next one, we're going to start examining how do I change the period of these graphs. Okay, we'll see you then. Take care.